Hello again, my dear students. Now it's the second part in our bipolar junction transistor lecture number 3. If you remember, in the previous part, we deal with the DC analysis of the MOSFET, or sorry, of the bipolar junction transistors. We first introduced the schematic of the bipolar junction transistors, either as a PNP or as an NPN. We try to understand what is the concept of, or how electrons are moving from the emitter to the collector, how current is moving from a collector to the emitter. And we study what we call the active forward mode. In the active forward mode, we have two conditions. We have that the emitter base junction should be forward and the base collector function should be reversed, as you can see here. And in this condition, we start to reach some important equation. The first was that the total current reaching the emitter is the summation of the current coming from the collector and the current coming from the base. And from here, we introduce the term beta as the common emitter current gain, which is the ratio between the collector current and the base current. Also, we reach another term that IC, or the collector current, equals to alpha times IE, which is the emitter current. Alpha basically equals to beta over beta plus 1. However, in most of the cases, we say that this alpha stands to 1 because beta usually is a big number, varying from 50 to 200. So in most of the cases, you can say IC is approximately equal to IE as far as you are working in what's called the active mode. So then we also introduce alpha as a common gain, common base current gain, and we start to sum up all these equations. We reach two models for the transistor. The first one was like that. Here you have the base. Here you have a diode representing the base emitter junction, and here you have a current source. This is a current dependent current source because the current here, depending on the current there by this equation, alpha is the current in the collector equals to alpha times the current in the emitter. Or we can have another form. Actually, we will give more focus about these two models in this lecture in the AC circuit. Again, you have a diode between the base and the emitter, which represents the emitter base junction. Now you have another current source. Still, it's a current dependent current source, but now it's dependent on IP by the factor beta. So beta times IP is equals to IC. So these are the two models. Then we study the IV characteristic curve. We distinguish between different modes, between the cutoff, the active, the saturation mode. The most important mode for us is the active mode, where we have one junction forward and the other reverse. However, we also understand what's meant by the saturation mode when we have two junctions are forward, or what's meant by the cutoff mode when the two junctions are reverse. And there is a fourth mode which is out of our interest, which is the reverse active mode. After that, we show up the three main configurations for the BJT, either as a common base, as a common emitter, or as a common collector. And we say that the common emitter is the most famous configuration for a BJT. Then we start to solve together three problems dealing with the BJT as a DC circuit. First, with supplying 6 voltage to the base, and we found that this transistor is working in the active mode. And then by supplying 6 voltage to the base, and then we found that this transistor is working in the saturation mode. And finally, when we grounded the base, and we found that this transistor is working in the cutoff mode. This was a quick brief for what we did in part 1. Let's now turn to part 2. In part 2, we are now interested to the AC operation of a MOSFET. I'm sorry. Now, if you remember, we had a typical slide in our MOSFET lecture, if you remember, when we directly connect an AC supply to the gate of the MOSFET. Now we are connecting an AC supply, but to the base of a BJT. If you remember, in the MOSFET, we say that in order to operate the transistor, there is a minimum voltage that should be supplied here in the base. If you remember from the previous section, we said that in order to work on the active mode, you have to adjust your base emitter junction to be forward. If this base emitter junction is reverse, then you are now working in the cutoff mode. So as a first step, this voltage should be greater than the built-in potential, which is 0.7 typically. However, this is a typical AC voltage, which fluctuates from a positive half cycle and a negative half cycle. So in the negative half cycle, your BJT will be by default off. And in the positive half cycle, where the voltage is still below the 0.7, again, this BJT will also be off. So this BJT will work only when the AC input is greater than the 0.7 voltage. If this AC is below 0.7, for example, if this AC is equals to 0.5 sine omega t, for example, then this BJT will be off all the time. That's why this connection will not work like that. You have to add a fixed DC supply in addition to the AC supply. Again, it's typically like what we did in the MOSFET lecture. So by inserting this constant VPE DC supply, you now guarantee that your BJT is working in the active mode all the time. And here the input is fluctuating based on the AC signal. This is again what we typically did in the MOSFET lecture. So as a result, now the total voltage across the base emitter junction is an addition of two different types of voltage. We have the V capital PE, which is the DC supply, and we have the V small be, which is the AC supply. This is a superposition of two different types of voltage. If we would like to calculate the current, there is an equation where we can calculate the current. Actually, this equation is out of interest for you. You don't need to memorize it. This equation that says that the I collector or the collector in the current equal to some saturation current multiplied by exponential EVPE over VT. Where VT, if you remember from the solid state electronic course, the VT is the KT over Q, which is the thermal voltage, which is around 25.9 volt. So the current moving again in the collector equal to the saturation current exponentially by the voltage drop on the base emitter junction over the VT. If you remember, this is typically an equation for a diode because this is simply a junction. This is simply a diode. So now you can remove this VPE and add these two terms. So we will have I saturation times EVPE over VT. Now it's the DC term times EVPE over VT. Now this is the AC term. But this term, which is I saturation times E capital VPE over VT, represent mainly the DC collector current. Simple. If you say that you don't have this AC source, it's just a DC. I mean, it is typically like this example. For example, now you have only a DC voltage connected to the base. So if you have only a DC source, then no V small VPE, and VPE is equal to V capital VPE. Then the current will move is equal to I saturation exponentially by VPE over VT. So this first term is the DC collector current we previously calculated in the previous lecture. So the AC current is equal simply to the DC current multiplied by the exponential EVPE small over VT. Now, if you remember, we had a condition in the case of the MOSFET to make a linear amplifier. Again, in the BJT also, we have another condition. When VPE small, which is the AC signal entered to the base, is much smaller than the VT, which is the 25 milli-electron volt. If this occurs, then you can use this mathematical approximation, and you can say that IC is approximately equal to I capital C, which is the DC collector current, multiplied by 1 plus VPE over VT. Again, if you remember in the MOSFET, we say that we have now two terms. The first term, which is a DC term, IC times 1 equals to IC, which is a DC term. However, the second term is an AC term because the V small VE is an AC term. And if you remember from the MOSFET lecture again, as you can see, I use the MOSFET lecture many times to make some sort of analogy or a comparison. So if you remember, if we insert a capacitor, this capacitor can get read from the DC and only pass the AC component, because capacitors are working as an open circuit for DC component. So simply by inserting a capacitor, you can have an equation like that. The AC current is simply equals to the DC current over VT, which is a constant, multiplied by the input. As you can see, this is a relation between the input voltage, which is VPE, the AC voltage, and the output current, which is the collector current. Now, this term, we have a name for this term since we study the MOSFET. If you remember, this is the term GM, or the transconductance. The transconductance is the relation between the output current and the input voltage. In the MOSFET, we make a relation between ID and VGS. Now, in the BJT, we have a relation between IC and VPE. And the constant or the slope of this relation is GM, which is the transconductance, which is equals to IC over VT. So this is a very simple AC analysis for our MOSFETs. Let's now turn to see how we can use this AC analysis in order to study the BJT working as amplifiers. Okay, now I will return to this model. I believe you remember this model. Few minutes ago, we showed this model. It was actually listed in one of our previous slides when we are talking about the DC model. It is very simple. It says that we have a diode between the base and the emitter. We are trying to make this diode forward, so you can replace it simply by a short circuit. And here we have a current. The current flowing in the collector is simply equals to beta times the current flowing in the base. This is the simple equation we know. And the current in the emitter is simply the addition of the current from the collector and the current from the base. As you know from the diode lecture, you can treat this diode either ideally as it is a short circuit, or you can say that it has a forward resistance, if you remember. So that will what we will do here. That's what we will do here. When we will replace this diode by a resistance, this resistance represents the forward resistance of a diode. And here we still have the beta times IB. This, what we can say, this is the DC model for a BJT. Now we need to have an AC model to the BJT. Based on the previous slide, we say that the AC current flowing in the collector is equals to GM times the AC input to the base. So simply we can make it like that. We can say that we have a current in the base, we have a voltage drop in the base, which is VPE. We still have a resistance, we will call it R by, or sometimes R small e. Here, the current flowing in the transistor or in the collector is GM times VPE, as we previously mentioned, and GM is equals to IC over VT, as we conclude in the previous slide. So this is simply the bi-model, or what's called the bi-model for an AC BJT bipolar junction transistor. Now you have a current source, you have a voltage dependent current source. This is actually the difference. Here you have a current dependent current source, it's a DC. Here you have a voltage dependent current source, which is an AC. Again, the resistance R bar can be calculated by this relation, which is R bar equals to beta over GM. You can calculate beta, and beta is given, and you can calculate GM, so you can calculate R bar. This model will be widely used in order to solve AC BJT problems, as you will see in the next part of this lecture. As we have a bi model, we also have another model, which is a T model. If you remember this T model, we already also studied in the DC part, if you remember this one, where we say that the current in the collector is equals to alpha EIE, which is the current in the emitter. So typically, we have it here the same. Here is the diode is replaced by a resistance. This is IE. The current here is alpha IE. This is the base, this is collector, and this is the emitter. Again, you can transfer it to this way. Now the current in the collector equal to Gm times VBE, which is this volt. This is the resistance RE, and this is Gm times RE. Gm is the same, which is IC over VT, but now this RE has a value of VT over IE or alpha over Gm. So we can use this model, which we can call it a T model, or you can use this model, which we call it the bi model. Both models will be used in order to solve the AC bipolar junction transistor lectures. Now, in the next part, my dear students, we are going to return to the paper. We are going to solve very two important configuration. The first one, which called the common emitter amplifier, as you can see it, and the second is the common emitter amplifier with emitter resistance, as you can see here. What we are going to do in the next part is we are going to solve these two circuits step by step using paper and pen in order to understand how we can analyze the BJT AC signals, AC circuits. Thank you very much for your concentration, and please, I'm looking forward to see you in the next part.